Okay, so let's get started. Hi, I'm Kohei Tokunaga from NTT Inc. I'm working on the WebAssembly host support in the QEMU community. Today, I'm going to share the state of WebAssembly support of QEMU. This is the summary of this talk. QEMU version 10.1 experimentally supports compilation to Wasm with Emscripten. It supports 32-bit gets with TCI interpreter mode as of now. And there are ongoing discussions including 64-bit get support and JIT backend and 9PFA support. I'm going to explain these topics in the later slides. So first of all, I will talk about the motivation of the WebAssembly port. The motivation of Wasm port is to open up new use cases of QEMU, even covering browsers. Expected use cases will include development environment and playing grounds, etc. And there are also existing application level attempts or works of porting them to browser. However, porting each software to browsers is not easy because it requires recompilation or re-implementation of the softwares because of the architecture difference or lack of some system calls on browsers such as fork and exec. I believe QEMU inside browser will enable wider range of modified softwares to run inside browser without software level work of porting. So QEMU version 10.1 added an experimental support for compilation to Wasm using Emscripten. Currently, it only supports 32-bit guests and in TCI interpreter mode, which is slower than other backends running inside browser. And there are ongoing discussions for further improvement, including 64-bit guests, JIT support, and 9PFA support. And this picture in this slide is an example of running Linux on QEMU 32-bit ARM emulator inside browser. So I will quickly show a demo of running 32-bit ARM emulator inside browser using the QEMU version 10.1. So this currently only enables TCI interpreter mode, so it is not so fast. It runs Linux and the BusyBox inside browser. And by executing uname command, you can confirm that this is the Linux ARM environment. And you can also see their processes running in this Linux system. And you can also see the root file system at /. So how to compile QEMU targeting Wasm? This command example on the slide shows the steps to compile QEMU into Wasm. The first command runs the configure script, and the second command runs the make command. Emscripten toolchains include mconfigure and mmake, which automatically set necessary environment variables for targeting Emscripten. And by executing this command, QEMU is compiled to qemu-system-arm.wasm binary file with some runtime JavaScript files. Now QEMU is compiled to Wasm. Then how to package guest images for QEMU inside browser. This command example shows an example of packaging as specified directly on the host into a format supported by Emscripten's runtime. So Emscripten provides a script called filepackager.py to package arbitrary files. And the above example packages a pack directly containing, let's say, guest images. And it produces QEMU-system-arm.data file and a loader.js script. And QEMU can access the images in the pack directly through Emscripten's file system. Then the Wasm compiled QEMU and the packaged images can be loaded to the browser. And you can pass QEMU flags using Emscripten's module object in JavaScript code. And guest images can be read via the Emscripten's file system. As shown in the code example in this slide, module object describes the flags passed into QEMU. Please note that their directlies called pack were named as pack in the flags, such as -l flag and -kernel flag, and they are the files packaged in the previous step. And the Wasm compiled QEMU now can access these files in the pack directly inside browser thanks to Emscripten's file system. So from this slide, I will deep dive into how this is implemented. First of all, how guest CPU architecture is emulated in QEMU. This is done by a component called TCG, or Tiny Code Generator. As shown in the right figure, TCG translates the guest architecture's binary into the host architecture. Here, IR, or intermediate representation, is used. So front-end translates guest binaries into IR, and backend translates IR into the host architecture. And here, TCI is an IR interpreter, which is one of the backends of TCG. And other than TCI backends, so other backends translates binaries in a JIT manner. So binaries are JIT translated into the host architecture, but TCI is implemented as an interpreter of IR. And QEMU version 10.1 supports compilation of TCI interpreter to Wasm. And JIT support is currently an ongoing discussion. Although Emscripten covers a wide range of common system APIs, there are still limitations. So several changes were needed for QEMU to compile using Emscripten. First one is there are no concepts of processes on browser, so fork-dependent features like demonizing or run with flags are disabled in the Wasm build. But please note that pthread is supported by Emscripten. So thread-dependent features like multi-threaded TCG or multi-core emulation are still available. And second one is aligned allocations uses POSIX memo line on Emscripten instead of using mmap plus partial unmapping of the region, because partial unmapping of an mmapped region is not supported by Emscripten. And third one is function pointer casts result in runtime errors on Emscripten, so its usage are removed. For example, glib relies on function pointer casts on some helper functions, so this usage are removed. Here, possible alternative approach will be Emscripten's emulate function pointer cast feature, but this changes function calling convention a lot. So this is currently incompatible to libFFI, which is an important dependency of Wasm build. So this cannot be used as of now. And another important component to be ported to Wasm was the coroutine backend. So QEMU uses coroutines for managing events in QEMU, such as IOs. And because Emscripten doesn't provide traditional coroutine mechanisms like uContext, so new coroutine backend needs to be added. And here, a new coroutine is implemented using Emscripten's coroutine mechanism, which is called fiber. This provides coroutine primitives such as Emscripten fiber init creates a coroutine, and Emscripten fiber swap switches to another coroutine. But there is an important limitation on fiber coroutine. So fiber doesn't support sharing a coroutine among threads, so which will require further changes to some devices relying on this behavior, such as 9PFS. So from this slide, I will show some ongoing discussions to make this feature more useful. The first topic is the 64-bit guest support. So QEMU version 10.1, again, only support 32-bit guests. And 64-bit guest support will require additional works. So to emulate 64-bit guests on QEMU, QEMU needs to be compiled targeting 64-bit host with 64-bit pointer support. But Emscripten's default target, which is Wasm32, supports only 32-bit pointers. Here, Wasm64 target can be used for enabling 64-bit pointers. And Emscripten provides two modes for Wasm64 targets. First one is memory 64 equal 1. This requires recent browsers with Wasm64 support. This is supported by recent browsers such as Chrome or Firefox, but it is not supported by Safari as of now. The second mode of Wasm64 on Emscripten is a compatibility feature, actually. By compiling with memory 64 equal to enabled, the program can run on older engines, including Wasm32 engines, with still using 64-bit pointers. But because they run on Wasm32 engines, the maximum memory size is limited into 4 GB. The next topic is a JIT binary translation support for the Wasm host. So this discussion is about adding a new TCG backend for JIT translation from IR into Wasm, and it targets Wasm64 to enable 64-bit guests. And WebAssembly cannot execute code generated on memory, so to execute the code on memory, browser APIs needs to be called. WebAssembly.module browser API compiles the Wasm code, and WebAssembly.instance API makes it executable. And this is actually a similar technique as used in other emulators on browsers such as v86 or QEMU.js, but they only support 32-bit guests as of now because they don't target Wasm64. And I will briefly describe how the binary translation is implemented. For details, please refer to the actual patch if you are interested in. So this backend translates each TB of IR to a Wasm module And TB is here translation block. This is a unit of instructions to translate. And Wasm backend translates an IR instruction into the corresponding Wasm instruction. As shown in the figure, an IR instruction at I64 is translated into Wasm's I64.add instruction, and each TCG register is mapped into a Wasm variable. However, Wasm instructions requires the operands are pushed onto the stack, Wasm stack, so these variables are pushed into the stack before invoking the instruction, and the result is popped from the Wasm stack after the execution of the instruction using global get or global set instructions. And different from other hosts, browsers come with some limitations for executing translated TB. The first one is compilation overhead of each TB Wasm module. And another consideration is browsers are not capable of a lot of active modules. So this makes it undesirable that translating all TBs into Wasm modules. So the number of Wasm modules needs to be limited somehow. So this backend enables both of a forked TCI and Wasm execution. TBs run on TCI interpreter by default, which is slower than JIT, and TBs running many times, like thousands of times, are compiled into Wasm. And I'm going to briefly show the performance improvement by the JIT support for the Wasm host. So I've measured the duration of compressing 10 megabyte random data using PIGZ on emulated x86-64 guest. So PIGZ is a gzip implementation with multi-processor support. I've compared the TCI backend and the Wasm JIT backend. Also enabled MTTCG, which is multi-threaded TCG or multi-core emulation. And please note that ongoing patches I've explained in the previous slides are needed to make it run on browser. So this is the duration of running PIGZ. So TCI takes about 252 seconds, which is very long because of the interpreter approach. But enabling JIT translation by the Wasm backend, the duration is shortened into about 35 seconds. And furthermore, by enabling multi-core emulation feature, which is called MTTCG, PIGZ performance improved more into about 16 seconds, leveraging multiple cores. And one more topic discussed is the 9pfs support. So this allows sharing data among the guest and the host JavaScript code. But 9pfs backend relies on coroutines for offloading the request handler to other threads. However, Emscripten's fiber coroutine doesn't support sharing a coroutine among threads. So here some changes will be needed to make 9pfs backend runnable inside browser. Finally, I'm going to show some more examples of running QEMU inside browser. So the first one is running x86-64 Alpine Linux inside browser using QEMU with enabling 64-bit guest support. And please note that this example requires ongoing patches explained in this talk. Okay. So I'm gonna log into this system as root, and by executing uname command, again you can confirm that this is a Linux x86-64 environment. And according to etc OS release, this is Alpha Linux. And you can also see the root file system at /. And another example is to run board device inside browser. This talk especially focuses on the Raspberry Pi emulation, as shown in the picture in this slide. So QEMU can emulate a variety of machines, including Raspberry Pi. So this example runs Raspberry Pi inside browser. And please note that, again, ongoing patches are needed to make it runnable. Currently, this is running BusyBox on the emulated Raspberry Pi board, and using uname command. Again, you can confirm that this is ARC64 environment, and you can confirm that CPU info shows this is Raspberry Pi board. So it says this is a Raspberry Pi board, and also you can get the board information on the sysfs. And this also says this is Raspberry Pi environment, and you can also see the root file system at /. So finally, aside from the topics covered in the previous slides, there are more rooms for improvement for this feature. And I've listed some of them in this slide. The first one is improvement for the Wasm backend, especially more detailed performance analysis will be needed, and improvement will also be needed, especially Wasm backend needs to be compared with other matured backends of TCG, and also disassembler support is also needs to be added for better debugging support. And another topic to be done is support for more devices like networking or GUI-related devices such as displays or mouse or keyboard. And for networking, one of the possible approach will be forwarding packets through using the browser APIs such as Fetch API or WebSocket API. And I've done some talks about this topic, so if someone interested in, please refer to the QEMU Wasm fork. And the third topic to be done is document and tests for the Emscripten build. Especially the important thing is we need to port the integration tests of QEMU into Emscripten. But integration tests currently depends on the features not available on Emscripten, so some work needs to be done to fully test the behavior of WebAssembly port. And also integration with the ecosystem, such as OS packages, will also be expected. Especially currently, most of the repositories like APK or apt are not intended to be accessed from the browser. But so, especially as many of them denies cross-origin access from the browser. So we need more repos allowing cross access from the browsers. So this is a summary of this talk. QEMU version 10.1 experimentally supports compilation to Wasm with Emscripten. It currently supports 32-bit guests and TCI interpreter mode, and there are ongoing discussions including 64-bit guests and JIT backend 9PFS support. That is all. Thank you very much. Do you have any questions? Yes, please.
In the JIT mode, how do you deal with the patching of translation blocks to link to each other? And if that happens, does the browser JIT do any optimization when it detects a hot path?
Thanks for the question. So the question about linking among translation blocks. Currently, so there is no feature of linking in WebAssembly itself. So currently, each TB is translated into a single Wasm module, and once the control entered into the TB Wasm module and then execute, and when it needs to link to other TB, it returns into the main QEMU loop. Not into the global QEMU loop. The loop is closed in the Wasm backend itself. It returns from the Wasm module and control back to the Wasm backend, and Wasm backend calls the linked TB or Wasm modules as a function calling. So this is currently the way how TVs are linked each other. And optimization, so because each TB is separated Wasm module, so I believe there are no global optimization among those TBs or those Wasm modules. But yeah, I'm not an expert of Wasm. I'm not an expert of browser optimization, so it needs more investigation how to improve the design of the TB Wasm module to make it performant on browsers. Yes.
Do you have an idea of the performance compared to native execution? Because we're going through WebAssembly, and I mean for the JIT backend you have right now, compared to the native QEMU, is it 5 times slower or 10 times slower or something like that?
I haven't done benchmarking comparing with native QEMU or against other backends, so I don't have exact number about this. But yes, this, as far as I run Linux systems on browser, it is much slower than native. But yeah, more benchmarking will be needed to identify.
Okay. Thanks.
You said there is a limitation of the number of modules, so when you translate a TB to a WebAssembly module, do you have a number of how many modules you can allocate to use, and what happens when you reach that limit? Is it a problem of the browser, or is it is it some limitation of QEMU not dealing with exhausted TB?
So the question is about so the number of limitation, or the limitation of number of modules inside browser. Yeah, as far as I run, recent browsers limit the number of modules into 10,000 or to 12,000 modules. And if the number of modules exceeds that limit, the tab like returns error like out of memory. And to avoid that, currently WebAssembly backend limits the number of modules into 12,000, which is a very heuristic value. And if creating another module can or possibly exceeds that limit, Wasm backend just do not instantiate that module. Instead, Wasm backend runs that TB on forked TCI interpreter so that new modules are not created. And also, Wasm backend deletes or removes some amount of modules running on the browser so that browser garbage collects these Wasm modules. Then Wasm backend detects that the garbage collection is completed. The Wasm backend restarts creating the modules again.
Hi, thanks for the talk, very cool. One question is, do you handle self-modifying code? And the second question is, you basically have a tier 2 optimizer in the JIT, let's say. So you initially use TCI, and if you see that a block is, a translation block is used many times, you switch to the more aggressive optimizer, which means WebAssembly. How hard was that? How hard was to implement that in QEMU? Did it fit well, or did you have to do a lot of hacks to have, let's say, this tier 2 optimizer?
Sorry. What was the first question? Sorry, I couldn't.
The first question is, do you handle self-modifying code?
Self-modifying code. So as far as so some backends does that is, so for example, when linking among TBs, so some backends has, currently Wasm backend does not handle any self-modifying code, because on the TCG backend level, self-modifying code is already abstracted away, as far as I understand, from on the IR level. So Wasm backend don't need to explicitly handle self-modifying code. Instead, Wasm backend or other backends as well needs to correctly handle the linking of each TBs. For linking each TBs, there are no need to deal with self-modifying logics. So WebAssembly backend currently, implements don't need any extra work for handling self-modifying code. And second way is about optimization.
Yeah, the second question is, you basically have a two-tier JIT engine. The first one uses TCI, and the second one actually meets WebAssembly. How hard was to put in place the heuristics to detect, now I need to do the more aggressive one? Does it fit well with the QEMU architecture, or did you need to do a lot of hacks?
So the design of current 2 tiers of optimization, it's currently closed in the Wasm backend, and currently, but as I said, Wasm backend currently forks a part of TCI interpreter into the Wasm backend, so that Wasm backend can internally handle both of interpreter mode and compilation mode. But yeah, thanks to by forking TCI backend into Wasm backend, currently all these like a 2 tiers optimization logic is closed in the Wasm backend. Thank you.